Okay, now let's talk about the Lax Milgram lemma. And before we do this, I would like to talk about bounded inverse. So I'll start with an operator A, which is such that A is greater than alpha I, alpha times identity, which means that A minus alpha I is a positive operator, and alpha is a non-negative constant. If we have this, then A is bijective, the inverse is bounded, and the norm of the inverse is bounded by 1 over alpha, where alpha is this constant up there. Now, why is that so? It is so because if you have an operator A that goes from H to H, and you have X in H, then AXX will be greater than alpha XX, right? By definition of what we have with the definite, with the positive operator, A minus alpha I is a positive operator, so what you have is this. Now, what we can derive from this is that alpha times the norm of X squared is smaller than AXX, that we know, but it's also smaller than the norm of AX times the norm of X, obviously, because we have an inner product here, so we have this inequality, which is always true. So from here, we can derive that alpha times the norm of X is smaller than the norm of AX. You can just simplify by the norm of X if it's not 0, and if it's 0, well, that holds anyway, so that's not a problem. So what we have here is that the norm of X is smaller than 1 over alpha times the norm of AX. Now, when we have this, we obviously have the injectivity. We have that if AX is equal to 0, then the norm of AX is equal to 0, because it's a norm. Then, because of this inequality, the norm of X is equal to 0, and because the norm is a norm, then X is equal to 0. So, as you can see, if AX is equal to 0, then X is equal to 0. A is linear, so we have injectivity. And therefore, what we have is that A inverse can be defined. Now, let me choose Z in the orthogonal to the range of A. And this means that Z with anything here, the inner product of Z with anything here, will be 0. So, for any y in range of A, we have inner product yz equals 0. Now, AZ is in the range of A, of course. Therefore, AZZ is equal to 0, which implies that we have this identity here. Alpha ZZ, which is smaller than AZZ, is going to be equal to 0. So we have the norm of Z, which is 0. Therefore, the orthogonal to the range of A is 0, which means that the range of A is the entire space, which means that it's going to be surjective. Now, Y being in the range of A will allow me to choose a X, which is going to be the A inverse of Y. And what we have is that A inverse of Y is equal to X, obviously, which is smaller than AX multiplied by 1 over alpha, which is exactly 1 over alpha multiplied by the norm of Y. So what we have is that A inverse is bounded, and its norm is bounded by 1 over alpha. Okay, now it's time to talk about the Lax Milgram lemma. Let me start with a Hilbert space H and a continuous and coercive bilinear form A. I will also choose F in the dual space of H. First statement, the equation for all u in H, the equation AXU equals F of u, will have one and only one solution, X. Second result, the application that associates the green F to the red X, which is going from H star to H, is linear and continuous. Why is that so? Well, because if you choose u in H, then AXU equals F of u is really equivalent to AXU equals ZU, because Z is defined from the Riesz representation theorem. You know that what you have is that f of u, f, can be identified to an element of the space, right? We can identify h star, dual space, and h. So when I choose a function from h to r, an element of h star, then you can really identify it to an element in h. So what I'm saying is that from f, I define z from the Riesz representation theorem. Now, since A is continuous and bilinear, there exists a bounded operator A from H to H such that AXU is equal to AXU. And what does this mean? The bilinear form AXU, which is here to the left, is equal to the inner product of AX, operator A, applied to X, with U. So it's an inner product here. Now, if you look at this and this, you have that AX is equal to Z. Since A is coercive, there exists a constant, alpha, such that A is greater than alpha I. Now, A inverse is a linear bounded operator. X can be defined as A inverse Z. So, as you can see, we can find one solution, and this is the only one solution we can find. Now, if A, the bilinear form A, was symmetric, which doesn't have to be the case, by the way, but I'm saying if it was, then we would have a very simple proof of the Lax Milgram lemma, because the bilinear form defines an inner product on H. Now, for any x in H, we would have alpha times the norm of x squared, smaller than AXX, smaller than c times the norm of x squared. So the norm here is the norm of the Hilbert space. So what we would have is that the norm associated to A would be equivalent to the norm of H. So H could be equipped with the inner product A and could be also a Hilbert space. Basically, H is a Hilbert space with both the inner product, natural inner product, and the inner product corresponding to A. And of course, by using the Riesz representation theorem, then we would obtain the result. The Lax Milgram lemma can be used and applied to situations that are quite complex. I'm going to give you an example where the application is to a problem which is not so complex. Basically, an ordinary differential equation, negative x prime prime plus x equals to a function g in 0, 1. And here, of course, the unknown is x. And what we're saying is that we're looking for a function x such that negative times the second derivative of this function plus the function evaluated at t is equal to g of t for all t in 0, 1. And we add to this that x prime of 0 and x prime of 1 are equal to 0. Of course, this will be for some g, and the function g will be in L2 of 0, 1. Now, what I will do is to apply the Lax Milgram lemma and prove that this equation has one solution and one solution only. Of course, many of you know how to prove existence and uniqueness of the solution to this equation by other means, but I'm going to just show you how Lax Milgram applies in this case, just to show you how we can apply it. So let's start by defining H, a space composed of all functions v that are in L2, such that the derivative is in L2. Let me also define AUV, a bilinear form defined by the integral between 0 and 1 of u prime v prime plus uv. So you take u prime v prime plus uv and you integrate it in between 0 and 1. And that is the bilinear form AUV, which seems pretty symmetric to me and also pretty positive. Good sign. Let me then define function f, which is the integral between 0 and 1 of u times g. And if u is in H and g is in L2, then f of u will be well defined because it's integral between 0 and 1 of a product of two L2 functions. It is also going to be linear and continuous. By the way, AUV is extremely well defined as well when U and V are in H. So this is a good sign. What we would need though is at some point to have H a Hilbert space, and we have a little bit of a problem here because really with this derivative we are not going to have H a Hilbert space, but the good news is that at some point we will have a brand new derivative. Basically in a few weeks from now we will have a brand new derivative that will make H a Hilbert space. So there is a hole in the proof here because of this problem with H not exactly being a Hilbert space, but that will be fixed in 2 weeks from now. So please bear with me, and we will have a new derivative really soon. Now, let's go back to our equation. Negative x prime prime plus x equals g. I can multiply both sides with any u in H, and that is still true, obviously, if the equation holds, and when I multiply both sides by a function u in H still holds. And if this is true, then I can integrate between 0 and 1, and it must still be true. Now, I can integrate by part. So what I will have is the first part of the integral will just turn into the negative x prime u in between 0 and 1. It means that negative x prime u will be evaluated at 1, and then I subtract the evaluation of negative x prime u at 0. Okay, and then this, this first integral, the integral on the left-hand side, provides on when I integrate by part, well, this term and the second term, which is the integral between 0 and 1 of x prime u prime plus xu. And this is equal to the right-hand side, which is unchanged, integral between 0 and 1 of gu, which should probably be called f of u at some point. This term is 0. X prime u prime evaluated at 1 is 0 because x prime of 0 is 0. And negative x prime u evaluated at 0 is also 0 because x prime of 0 is equal to 0. So what I'm left with is axu equals f of u for every u in H. Now let me put some color and just remember what we just said a few minutes ago in this video. We just gave you Lax Milgram, the Lax Milgram theorem or lemma. And you can see we're exactly in this situation, provided, of course, we neglect this little hole we have with H for the reason we said. And in this case, what we have is, existence and uniqueness of the solution to the ordinary differential equation, which is on top of the screen here. So, as you can see, we use Lax Milgram in this case, and it provided us with a result.